Here we are looking at sums and scalar multiples of matrices. Now this is going to help us to draw parallels between vector arithmetic and matrix arithmetic. So to get us started, I want to begin by recalling what makes two or more matrices equal. So two or more matrices are equal if they have the same exact size. So if they have the same size. So size implying they're both going to be m by n matrices. So this means that their corresponding columns and entries are all equal. Not necessarily the equal scalar value, but equal in size. So the first algebraic operation with matrices that I'd like to explore together now with you is that of matrix addition. So if A and B are both m by n matrices, then the sum matrix A plus matrix B is also an m by n matrix whose columns are the sum of the corresponding columns in matrix A and matrix B. So what exactly does this imply? Let's explore. So to begin, let's let A and B be m by n matrices. By definition. So then what? So then we have matrix A plus matrix B. And let's think about these individual matrices on their own first. So you have matrix A. So matrix A has column vectors A sub 1, we have column vector A sub 2, all the way up to column vector A sub n. So there's matrix A, and now we want to go ahead and add matrix B. So matrix B has the column vectors vector B sub 1, column vector B sub 2, all the way up to column vector B sub n. Now, since these two matrices have the same size, we can add their corresponding columns. So in other words, we're going to add the first column vectors together, we'll add the second column vectors together, and we continue with this method all the way until we get to the very last column vector. So this is going to leave us with a resulting m by n matrix whose first column vector is the vector A sub 1 plus vector B sub 1. The second column vector will be defined as vector A sub 2 plus vector B sub 2. And we continue merrily along all the way until we get to that last column vector A sub n plus vector B sub n. So we're adding, or we're taking the sums of the corresponding columns of each matrix to end up with a matrix of the same size. So that's matrix addition. And the second algebraic operation with matrices I'd like to explore now is that of scalar multiples of matrices. So if C is a scalar and A is a matrix, then the scalar multiple C times A is the matrix whose columns are C times the corresponding columns of matrix A. So again, to illustrate this, let's let C be any scalar, our little heart's desire, and we'll also go ahead and let A be a matrix. Any size matrix you want. So then what? So then, the scalar multiple, C times matrix A. And let's think about how we define matrix A here. So C remains as it is, and we know that matrix A has the column vectors, vector A sub 1, column vector A sub 2, all the way down to some arbitrary last column vector, say column vector A sub n. Now, by the distributive property, we can take this scalar C and distribute it through to each entry of the matrix, each column of that matrix A. So we are left with the matrix C times column vector A sub 1, then we have C times column vector A sub 2, all the way up to that last column vector, C times column vector A sub n. So we can see here now that each column vector of the original A is C times as big. And so this is the same idea that we see with vector addition and scalar multiplication of vectors. So now that we've established these two definitions, let's go ahead and look at some examples.